Let's wait for 1 more minute. Let everyone to join. After that, we will start the session. Okay, let's start the session. My name is Satyakam Pratap Singh, and I am PMRF scholar and NPTEL TA for the course This Smart Grid Basic to Advanced Technologies, whose instructors are Professor N.P. Padisar and Professor Premlata Janaman. And this is the 10th tutorial session. Okay, and so we will go through the some of the topics which is important for solving the assignment, 10th assignment. So make sure that you listen the properly, and if you have any doubt, let me know while the session itself. You can open your mic and ask me, or you can write in the chat box itself. Okay, so let's start the session. So I'm starting the session with the certain transformations techniques such as the Clark's and the Parkes transformation technique. So this is also very important for designing the control systems and all control system for uh, control systems and the other architecture inside of the grid connected system. So coming to the why the need of this Clark's and the Parkes transformation is there, the performance, if you see that the performance of the three-phase AC system, which is described with the voltage equation, such as the voltage, if you know that, Vm is equal to Vm sine omega t, if you're considering the A phase, then you have B phase, such as the Vm sine omega t minus 120 degree, and you have Vc, that is the Vm sine omega t plus 120 degree. In the phasor, if you want to represent it as, this is the actual representation in the phasor, that is the VA, VB and VC. If you see that these voltage equations and the inductance, that is the inductances are dependent upon the rotating frame, and this sum machine have the are the function of the rotor speed itself, because when the rotor have the winding and it rotates, okay, then in that function the reference frame of your EMF which is being developed, it rotates. So for that purpose we use this class and the past transformation to make a stationary frame. Okay, because if you see that in the synchronous generator itself, if you remember that it is the EG angle delta, and you have certain EMF, that is XG and VT, and you also have inductance, then the terminal voltage is there, that is VT. And this term which is have the X term, it is actually the self inductance and the armature inductance summation, that is XAR plus XS. And this XS is actually LS minus M. LS minus M, and this M comes with the function such that you have two windings. First is on the stator, and second is on the rotor. Rotor you have the field winding, and on the stator you have armature winding, if you remember that. So there are certain interactions in between the stator EMF and the rotor EMF, from which the certain EMF got induced due to the mutual flux interactions. So that is actually the self-inductance, that is Ls minus M. Ls is the self-inductance of the stator winding, and M is the mutual inductance which come from the rotor side field winding. Okay, so a change of the variable is often used to reduce the complexity of this differential equation, and there are several different methods for this transformation variable to make it an synchronously making the synchronously rotating frame to a stationary frame. So Clark's and the Parkes transformation are two of them, and there are actually very much important importance also of this kind of system. So coming to the first transformation, that is the Clark's transformation, if you see that you have three windings, suppose A, B and the C, and these are all are rotating. That is a what I have shown also, that is a VA is equal to Vm sine omega t, and VB is Vm sine omega t minus 120 degree, and VC is the Vm sine omega t plus 120 degree. Okay, so there are certain time instants are there. Suppose this is a time dependent term, first one, second is also time dependent term, and VC is also time dependent term. So at t is equal to 0 and t is equal to say pi and t is equal to 2 pi, these all values, that is a VA, VB and VC going to change. So this is the basic concept, that how to utilize this class transformation to make it as a time varying, time independent feature. Okay, how it can be done. Suppose this VA is VM, okay, and VM angle 0 degree, I'm taking the maximum value. So and the VC, if you remember, that is minus 120 degree, depending upon this situation. Actually this is at B and this is C. So VM angle plus 120 degree. Okay, so if you means break it in the two components, if you see that this is the x-axis if you take, and this is the y-axis. If you break this VM angle 120 degree, what you will get? You will get that VM cos of this, cos of 120 degree, depending upon this angle, and depending upon one component on the y-axis and one component on the negative axis, minus x direction. And same with the VC. If you take the two components, one will be orthogonal and one is similar in the x-axis direction. And the alpha axis term is already on the x-axis. So what you got? You got the two components which is actually on the two axes only, not on the three frames. So this is the alpha beta direction. So you will get one terms from the A part and one from the VB and one from the VC. So these are all the summation of the vectors of this VA plus VB plus VC. Okay, and same with these beta components also, that you will get some components of this synchronously rotating frame on the beta axis also. So both this alpha and beta are the orthogonal to each other, and if you see that there are no dependent terms of the time frame. So all time instance, all the components are in two direction only, in the alpha or the beta. Okay, so these are the two basic concepts for converting this synchronously rotating frame, that is ABC frame, to the alpha beta frame. Always remember that for conversion of this ABC frame to alpha beta, you actually use this class transformation. Okay, what is trick to remember that? If you remember this is Clark, capital C, and alpha, if you see that this is beta, so A, B, C, if you can remember from that for converting to the alpha beta frame, you use class transformation. Mathematical representation of this is like that. You uses one zero synchronous sequence components also into that, because it is a T3 frame. The three frames are there, that is a three phases. So you need one more component, that is zero component, when there is any unbalanced system is there. So f alpha beta 0 is the T alpha beta 0 multiplied by the f ABC, which is synchronously rotating frame. So this is alpha beta naught is the alpha beta and the naught, and ABC f ABC is the FA FB FC, and there is transformation. And F can be anything, that is the voltage, flux linkage, current or electric charge. So T alpha beta is represented by this equation, that is 2 by third of this 1 minus half minus half. This comes with the same when you distribute this B component on the both axis and y axis, then this transformation will come, and which will be constant. Okay, so FABC, from here you can also convert from this ABC to alpha beta or alpha beta not to ABC. This both can be transformable. Okay, so coming to the second part, that is the Parkes transformation. This is also a very important terminology or the transformation techniques. Why? Because if you see that there are two frames I have considered, that is the ABC components initially it was there, and I have defined two components, that is alpha and the beta. What happens when the this all alpha and the beta terms are also rotating like that? Vm is angle sine omega t plus theta plus 120 degree kind of thing. So theta terms are also there, okay, and the omega t terms are also there. So what you happen that you have to synchronize with the system with this omega t, okay. So if suppose there is rotating frame and it is like that, and your system is rotating like this, and this is the component, that this is the D component and this is the Q component, okay. D component is leading with the alpha with the certain angle theta, and the B, this Q component is also leading with the certain angle theta. So how you define this? For the definition of this rotating frame of the alpha beta also, you do this Parkes transformation. So what happens that you converted initially with the ABC to alpha beta naught, then you can convert to the this DQ naught frame, and this DQ naught frame actually needed this omega t term, not in the alpha beta naught. By this don't need any synchronously rotating frame angle. So how you actually implement that? We actually take the VABC as a reference, then we fit it to this PLL, and PLL gives this measurement of the frequency and the theta component, okay. Then you use this theta to implement inside of this DQ naught frame for conversion of this ABC to DQ naught, but you don't need anything for the alpha beta frame. And same with this when you are converging from DQ naught to ABC. So this is a concept of basically the Parkes transformation. Mathematically, it is represented by this equation, that is the F dq naught is equal to qd naught and FABCS, and same with this, that qd naught is the FQS, DS and naught S, and the FABS is the FAS, FBS and FCS is transformation. And this is the equation. If you see that TQD naught S, this is the function of theta. This is a function of theta, but not the time. Okay, this is the important point, that it is a function of this rotating frame, but it is not function of time. And theta it can be derived, that is omega is equal to d theta by dt. That is same. That is theta is equal to angle of this omega and d omega dt. Okay, so by that you can get this omega dt, and you also can define that theta naught which was initially can be there, okay, which is constant. And you can also convert from this ABC to DQ naught, and from the DQ naught also convert to the ABC as well. This is the two most important, this Parkes and the class transformation. For the important point are, you have to remember that where to use. So what I've told, ABC to alpha beta, you use Clark's transformation, and for conversion of ABC to DQ naught, you use Parkes transformation. Okay. Always remember that capital P, Parkes is capital P, and the DQ naught you have Q. So from that you can remember that Parkes, which to use. Okay, so if you have any doubt, you can ask me in the between by opening your mic or writing in the chat box itself. Okay, so before jumping to those microgrid operations, I wanted to highlight few of the power quality issues which already been discussed in this NPTEL sessions also. So I wanted to highlight few things, that this power quality issues is a major concern. Major concern why? Because you have a different kinds of components, and the different nature of the components are also there. Why? We have a power system components, and currently we use this power electronic components. Okay, this is of high power level, and some components which is of low level also, that is the low electronic devices. We also use some of these communication features are also there, where this time lag, time delay kind of things comes into picture. So power quality is a combination of this voltage quality and the current quality. So by defining this voltage quality and the current quality, you actually define this power quality, and this is a concern with the deviation of the voltage and or current waveforms from their ideal sinusoidal waveform of the constant magnitude and the constant frequency. What do you mean by this? If you have suppose you have a VA, VB, VC components are there for the voltage magnitude. If you are getting the pure sinusoidal waveform, that is the VA, VB and VC with the 120 degrees shifted, so this is fine. That is fine, that this your waveform quality is actually good. Okay. What are the parameters to take? First is the TSD is there, one of the parameters to check. Where there are multiple TSD definitions are there. One is normally which we use, that V0R1, that is the V0R, one of the component. Okay. So TSD is basically defined the sum of the components of the second, n is equal to 2 to infinite components, that is the AM square, and divided by this AM1. Okay. So this is the basic TSD definition. Percentage TSD means multiplied by 100. So if this deviation can be, if there is any deviation is there, you represent it in the form of this sinusoidal component, the summation of the sinusoidal component in terms of the harmonics. That is, the fundamental is actually useful, and the other DC components and third harmonics and the fifth harmonics and the sixth harmonics, these are actually not desirable. Okay, they actually create the heating in the system. So what are the important power quality problems and the causes are? First one is the voltage sag. This voltage sags in the can be caused due to this line faults, starting of the large induction motor and the switching on the large devices. And the what method of characterization is the magnitude and the duration. How I'm saying that? If you see that what is there, actually there are two, suppose these two bus bars are there. Bus bar 1, V1, and the bus bar 2 is there. What you need actually, you need that there should be always a flat profile. Flat profile means if you are injecting 230 volt, this 230 volt will also reach without any deviation in the RMS value. But what happens that this voltage got means lower down at some point, and then got it is 230. Okay. So in between the points, this voltage got sagged up. Sagged up means it is lower than the 230 value. Okay. And there is a one situation also there where the voltage swells. Swells means voltage higher in between at some points, and it lowers down. Okay. So this is the kind of two system are there. This is a voltage swell, and second is the voltage sag. Okay. And the voltage swell occur due to the capacitor bank switching. Why? Capacitor bank have the capacity to boost this voltage. Why? It can supply the reactive power, instant reactive power at a certain point of time. So because of that, you also remember that Q is strongly coupled with voltage and weakly coupled with delta. Okay. And power is strongly coupled with delta and weakly coupled with voltage magnitude. So that's why in the fast decoupled method, we also take this delta P divided by delta del P del V and del Q del delta and del Q del V. Okay. By that we actually define the which components are actually more means related to the particular terms. Okay. So in the capacitor band switching, the sudden instant of reactive power injection can make this voltage swell condition. In this also affect this magnitude and the duration, up to what time it can happen, and the magnitude how it is higher than the normal operating conditions. Okay. Third is the voltage interruption. Voltage interruption is that suppose that you have a temporary fault. Temporary fault, suppose a tree branch got fall on certain line and you got LG fault, or you get dead short circuit fault. Dead circuit if all the lines got tripped, touched at a particular moment. So the duration of this characterization is also important, because you have certain auto reclosers and other mechanism that based upon that you can temporarily make the system to work in the faulty situation. After that you make the system to come back into the normal situation. If the normal situation not arrived at a particular duration at which you want, it means that it is a kind of permanent fault, and you have to change the line or the do certain kinds of arrangement to get away from that. Okay. And the fourth point is the harmonics. Harmonics come from the non-linear road. Non-linear roads means you have a multiple types of load. Suppose you have a oven in your home. you have oven is actually heating load that do not actually affect much, but you have this trim lights are there, you have the tube lights which have the power electronic converters inside of that, you have the BLDC motor for the flux change and all. So there are different kinds of load, non-linear loads are there. You have a diode, you have MOSFETs. So these are the non-linear sources. And based upon that non-linear loads, it then the harmonic injection come into the picture, and that harmonic get injected into the current into the current which is coming from the grid. Okay, so it distort the current which is coming from the grid also. Adjustable speed drives, AC drive, SMPS, mainly most important is the power electronic converters. Okay, power electronic devices which is mainly causing this harmonic problem, and it is actually characterization problem in TDD and the TSD and the harmonic spectrum. Okay, and the certain notches is also there. Notches, in what do you mean by notches? If you see that in the figure itself, this is the, suppose this is a pure sinusoidal. What happens that at certain point you got a certain spike at the particular situation. Same with this in the negative direction also. So this notches is also a problematic for this power quality, because you want this pure sinusoidal signal. At a particular times this sudden notches can come, it can damage the insulation in the voltage, and it also means affect the this wire itself, because this is have a certain capacity, that thermal limit is there of this certain wires. So if you are if you are getting the notch into the system, then it can impact this insulations and the this wire itself. Okay, so mainly it comes to the power electronics converter when you do the switching itself. So this is also represented based upon this TSD and the harmonic spectrum. And the other is the transient. Transient is also one of the phenomena when it is actually a temporary kind of situation. When you sudden switch on the heavy loads, then it actually take the current, higher current for creating the flux and all, and also in the situation of the temporary fault. So these transients are the very actually not desirable when the initial situation come for the flux generation and all. And this is also defined in terms of the magnitude and the duration. And the seventh and the last is the unbalanced loading. Unbalanced loading is actually also there. In the distribution system, we also have this three-phase system, and the single phase come to this our household. And there is a lot of mismatch between the actually the current rating in the each phases. So that create a unbalancing, and for that because of that region, your neutral wire has to of a higher capacity to sustain this unbalanced loading into the system. This also comes with this traction kind of thing, arc furnaces, and this also this inject the negative sequence component and the neutral current. So neutral actually handles this kind of unbalanced situation. So there is also a certain rating involved with these neutral wires, which also have a certain capacity and the heating limit, that is the I square R T limits. If there is a lot of unbalance, so negative component will mostly flow through the neutral, so it will increase the heating in the neutral wire itself. So these are some of the kinds of voltage this power quality issues are there. Suppose if you see that this V rated is there, V rated condition, if you see that this is actually a normal situation there till this 0.05, this 0.05 second, this normal voltage are there, that is a VA, VB and VC, and all are symmetrical with a 120-degree phase shift. Suppose the voltage sags come, a sudden drop of voltage you can observe into the system. Okay, same happen with the voltage swell. If you see that the voltage rise in the voltage at particular situations. Okay, and the voltage interruption is that sudden drop of the voltage maintaining going to zero in the all situation. Okay, and if you see the current related power quality wrong, that is a use. If you see that this is a rated power quality, this current, that is a IA, IB and IC, and these all are symmetrical, which we desire actually. It should be of a particular magnitude and the RMS value which we want, and it is 120-degree phase shifted. But what happened with the non-linear loads? If you see that This is not a sinusoidal waveform, and if it is a not sinusoidal waveform and it is periodic, so it can be represented in terms of this number of harmonics which are actually there in the sinusoidal components wise. Okay, so this type of waveforms inject the lot of harmonic into the system. Same if you see the in the notch situation also, this is a kind of notch. If you see that this notch came and this notch is there, this notch is there, it can impact this insulation level and the current carrying capacity, that the heating limit can exceed the heating limit of the wire. And if you see the unbalanced loading, if you see that the voltage magnitude of this Vy is higher and the Vb is lower and the further lower of the Vr, this is also a kind of non-desirable situation. If you see this harmonic component, I harmonic in the E situation, this is also a non-desirable. A lot of harmonics are there that can impact your system a lot. Okay, suppose in the F situation, if you see that first phase got interrupted. This is a B phase got interrupted into the situation, and it also have a certain kind of jump in the phases also. So this kind of system, suppose the normal operation is there, you sudden switch it off, then it go directly to the zero, not following this path. So sudden drop. So what happens to the stress to the power electronic component that inject the DC component and the other harmonic into the system. Okay. So these are the certain power quality issues into the system. Based upon that, I have put it one question on that. Please feel free to try this question based upon TSD level. Okay. If you have any doubt, you can ask me in between by opening your mic and or writing in the chat box also. Okay. So please try this question. I'm giving you 5 minutes to solve this question and think of it. In case of any doubt, just let me know. Okay, and try to solve this question. This will boost your confidence also and also your understanding towards these topics. I need at least one answer from you guys so that I can proceed further. So in case of any doubt, you just let me know. You can just use your logic that okay, RMS value of the harmonic is 20 amps. I got one answer from the Gautam. Okay, thank you Gautam. That is Gautam is saying it is 20 amps. Anybody else who is trying? Shruti, Akash, Devendra, or Shibna, anybody? If you have any answers. Okay, let me jump to the solution part. Okay, I got one answer. So actually the TSD definition, before starting this numerical solution. So if you see that TSD is actually defined in terms of 1 upon g square minus 1, and g is the v0 r1 divided by v0 r. You can write also in the terms of this v0 r2 square, v0 r3 square plus dot dot dot, or divided by v0 r1 square, or you can also write in the form of v0 r square minus v0 r1 square divided by v0 r. Okay, there are multiple ways to write depending upon the what you are having in the question, what you need. Okay, so it is saying that TSD is 0.1, this is okay. And also saying that it is also having the RMS component of the fundamental components at 200 amps. It is fine. And this is the actually they wanted to know the RMS component of the harmonic actually. Okay, so in this situation, if you see that v0 r2 square plus v0 r3 square plus dot 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 the v0 rn square, and this terms I am considering as p. So p is have to be 0.1 multiplied by 200, that is actually 20 amps. Okay, so how you will get this p? So you have to think that which is harmonics are actually prominent. Okay, so suppose I am having only second harmonic component. Okay, that's fine. So if the second harmonic component is 20, it means that the root 20 square can be 20. Okay, is it can be one of the answer. So suppose it have a this RMS component of harmonics is 40. 40 means it have to be 40 square. So that's why 40 square minus certain component, then you can get this 40. Okay, okay, are you getting my point? That 40 square means you have to subtract something from the situation. After that you will get 20 because you have to get this 20, but there is a no negative terms are there because at all are the square terms, so you don't have any negative term. Same with the situation with the 60 also. In the 60 for getting you need to 60 square or minus something so that you can get the 20. Okay, so this 40, 60, 80 components can be discarded. Okay, so the answer is 20 amps. Why? Because only thing is that you will get 20 square, root 20 square as a 20 and only one situation, not in the other situation there 40, 60 and 80. Okay, if you have any doubt you can ask me. uh, okay, let's move to the further topics, that is the harmonics, what is the causes and what is actually the mitigation techniques. Causes are actually what I have told, this is non-linear loads, power electronic switches such as the adjustable speed drive, that is the AC DC drive, and the SMPS arcing device and etc. And what are the impacts? Impacts are the harmonic current produced by the non-linear loads are injected back into the supply system. That is actually problematic. Actually, if the harmonic is generated by this load terminal and it got actually consumed itself at the load terminal, that is not problematic, but it is getting injected into the supply system. Okay, that is problematic. Second thing is that this current can interact adversely with the wide range of power system equipments connected on the same network. That is also because if you have a non-linear load and you got a certain distortion, certain spikes, and you are injecting and some other, suppose you are injecting reactive power at that particular point, so this voltage which you are needed, that also will have this spikes, so that is not desirable. So coming to this third part, that is specifically with the capacitor, transformer and the motors causing additional losses, overheating and the overloading. And the overloading in what sense? Because a sudden increase in current will be there. Suppose the sudden spikes, certain notches are there, so that can impact and create a sudden high overheating into the system. Okay, and the fourth, if you see that this harmonic current can also cause the interference with the telecommunication line and the errors in the power metering and the controls. That you already remember that transposition technique which we do in the transmission lines and all. So based upon that also you can get this, suppose you have a only one system which is not being transposed, so the flux induced between the two wires can be differ in terms of this proximity effect and the Faraday effect. So that is also can kind of that is also kind of problematic. Okay, so you got flux linkage in between these transmission lines and the this communication cable on the same, which is mounted on the same line. Okay, so that is also a problematic. So these are the some of the effects, and the mitigation techniques are you have to use certain filters for the mitigating of this power quality issues. Suppose you have this passive filter as such as shunt, series, and the hybrid system. If you see that the A component, A have the LCR filter is there, LCR filter which have a certain resonating frequency, and the this heating loss is there in the terms of R. Same if you see that the B part, that is a tank circuit is there. Tank circuit the have a certain resonance between the L2 and the C2, and then also the this heating can happen. Okay, and the same with this one kind of this shunt and the hybrid system. These are also kind of passive filters. Basic concept is that you have to filter the harmonics. What kind of harmonics? Lower order harmonics in some situation, and the higher order harmonics based upon the certain situation which you need. Okay, so the higher order harmonics I have no actually not actually problematic in some sense. Suppose you have a 32 at harmonic, 33rd harmonic, that is not problem because the current is very low in that situation. The I divide by 32. Okay, so root 32 kind of thing. So certain shunt active filters are also there, D as statcom what I have been taught, and you also have a certain capacitor bank. Automatic power factor correction is also there into the system during this non-linear road. Suppose the non-linear roads have certain harmonics, you inject certain reactive power component to improve this non-linearity behavior, or you can consume the extra reactive power which is occur into the system. Third is the series active filters are there, that is the DVR kind of system. You have VDC here and the active filter, and you have certain coils for transforming the voltages between the system, so that suppose you have a VT voltage and you can reduce that a VT by N. So this component have a lower rating based upon this series active filter and DVR system. And the fourth, you can use the UPQC. There is a combination of the shunt and series. This is actually a series kind of system, and you have a shunt also. Okay, so both types of system can be hybrid system can be implemented into system. Main thing is that you have to improve the power quality. Okay, so if you see that this is the actual the situation which happens, that is the, if you have a utility grid and you have a load, this load utility grid can create this power quality into the loads, and load can also create the power quality issue into the utility grid. And but the voltage quality into the utility grid is reflected into the loads. Okay, so the voltage mechanism which is being controlled is having the parameter linked with this utility grid. Okay, and this current quality basically it is defined in terms of the loading conditions. Okay, it inject the this harmonics into the utility grid, but the voltage quality it is from the utility grid to the load side. Okay, so these are kind of power flow management. If you see that power flow management, if you are having the active power filters, power flow management between the load and the power flow management, and same with this utility grid and the power flow management. And this is also have a certain feature which is communicating with this real energy sources that is delivering maximum power, compensating the energy fluctuation between this storage system. So that is also this active power filter, this actual in between management can handle all the situation, that power flow management, quality issues, current quality, power quality, voltage quality, and also it can provide this power flow management between this storage system, renewable energy sources, or in between the utility grid and the load. Okay, so this is the first module, and if you have any doubt you can ask me till now. After that we will move to this second module, where that is the hybrid AC DC microgrid. Yeah, if you have any doubt you can ask me now. Okay, I think there is no doubt. We can discuss in the last also if you have any doubt. In major problem can be there. So, coming to this hybrid AC DC microgrid, if you, from the name itself, you can see that it have the both system, that is the AC components and AC power generating sources and the DC power generating sources, and this is the combination of this hybrid AC DC microgrid. In the previous sections, we have discovered that AC microgrids, DC microgrid, and this topic were left, that is the hybrid AC DC microgrid. So if you see that this is the AC load is there, and you have a certain AC generating sources such as this gas microgrid micro turbine, and you have this PV system. PV system is there which is DC but is connected to the AC feeder. AC feeder is connected to this AC feeder. So you have to convert this DC component, DC power of the PV generation to the AC for connecting to this AC feeder. Same with this ultra capacitor. Ultra capacitor for giving this power from the DC to AC, you have to connect to this AC feeder. So main thing you have to remember that this PV generation is unidirectional. Unidirectional power flow is only possible in this PV generation. Okay, so and also there is a one MPPT terms is there which I have actually taught you in the previous sections, previous tutorial sessions, and this MPPT is adjustable based upon the load. Suppose you have a PV generation of 2 kilowatt, okay, but you have a load capacity, load which is also connected, and it have a only 1 kilowatt capacity to absorb. So this MPPT will try to make this 2 kilowatt to actually generation capacity up to 1 kilowatt using this MPPT. So you don't have to need to install a additional system to absorb this 1 kilowatt. If it is a grid connected system, then fine, you can send this 1 kilowatt directly to the grid. So if you have a islanding situation and you have a don't have any absorbing powers phenomena inside of this closed loop environment, then you have to use this MPPT control inside of this PV generation. Okay, so this is a kind of system I wanted to tell you. And second is the ultra capacitor. Ultra capacitor, one thing, and the battery storage. These two are the bidirectional. This can absorb the power when the power is in access into the AC feeder, and it discharges when the AC feeder cannot maintain this voltage rating of the system. Okay, so these are two kind of bidirectional power flow situation can happen. Same if you see that this is a DC feeder is there. DC feeder, it means that you have to connect only DC components with there. If you have any AC system, you have to convert from AC to DC. You have a EV into the system for charging the vehicle, that is a G to V or V to G or V1G. This kind of system you need a certain kind of DC DC converter. Same with the DC load home and the DC load in the hospitals, and the wind power generation converting from AC to DC. Same with the battery. And after that you have this this main grid. Main grid have a certain bus bar which is connected with this DC power DC microgrid with a certain DC to AC converter. Okay, AC feeder can directly connect to this AC this bus bar because it is actually AC, but for converting through the DC feeder to this AC mains, you have to convert from DC to AC. Then you have a switch and the point of common coupling between the utility and this microgrid and the substation. Okay, so this is the basic main architecture of this hybrid AC DC microgrid, and you have a certain possible networked hybrid AC DC microgrid situation, that is the physical system and the communication requirement. These all are the physical environment. Okay, so if the communication happening between this wind power generation and the utility grid, that is the communication layer. That is actually above of this physical system. This is your physical system. Okay, and this is the above layer is the communication system, and this communication system have a multiple component communication between the AC microgrid, DC microgrid, AC microgrid 2 and the DC microgrid 2, and also the there's independent this couplers also there, three-phase DC generation sources, and in between many communication features are there. So these are the two types of systems are there. One is the physical layer and second is the communication layer, and both have a certain advantages based upon this generating sources. Okay, So coming to this types of converters which are employed for this interfacing, that is the two types of converters are there, which I have told you, that is the interlinking capacitor. If you have a AC feeder and you have a DC generating source, then you have to use this DC to AC converter in between for connecting. Suppose you have a DC microgrid and DC feeder, and you have a AC generating source, then you have to convert this AC to DC. And you have a DC can directly be connected to DC feeder, or AC can directly be connected to AC feeder based upon the voltage and the rating which have to be seen. This is generally referred to interlinking capacitor, that ILC, interlinking converters, and the works on the principle of equalizing the DC side per unit voltage, which I will explain in the further slide. And second is the back-to-back converter. This is generally referred to add BTBC, which is implies the reference setting control on the both sides. Okay, this we will read in the further slide. So you actually have to remember that there are two types of interfacing converters are there. One is the interlinking capacitor converters, and second is the back-to-back converter. Okay, so coming to this structures of the hybrid AC-DC microgrid, if you see that this is the utility grid, and you have AC bus in between. So for that, if you have a DC load, you have to convert from AC to DC, and AC load can directly be connected, and you have a certain storage element or AC distributed generator or DC distribution system. So you have to convert from DC to AC or AC DC to AC based upon the power level requirement. Okay, and the storage system has the bidirectional converter which you need, that also needed when the power is excess, you have to charge that, and when the lower power generation there, you have to inject the power. But that is not case with this DC coupled hybrid microgrid. You cannot connect only DC bus bar and convert into the AC and directly feed to the grid. There are certain interfacing converters are there for conversion of this power, because each converter have the power capacity and the voltage capacity and the current capacity. So you have to employ the multiple sections of the DC to AC converters for the employing and the connecting with this AC utility grid. So if you see that this is the AC bus bar which is connecting to the utility grid, and you have a DC bus bar which is connecting with the DC generation system, AC distribution generation system, and the storage system, and which is connected to this DC converter, AC DC converter, and the bidirectional converters. And you can also connect this DC load directly to this DC bus, but for the converting to the AC load, you have to convert from the DC to AC in between the interfacing converters, then you can inject the power to the AC bus bar. Okay, so this is main point is that this AC coupled microgrid have the various DGs and storage equipments are there connected to the common AC bus bar through the interfacing converter. Okay, this is the interfacing converters. And if in this DC coupled hybrid microgrid, these DCs are connected to the common DC bus bar, but you have to need this interfacing converters. These are the interfacing converter. So this is the actually main crux, that this is the back-to-back interfacing converters, and this is also the interfacing converter for conversion. Okay. And coming to these structures of the microgrid, if you see that this is the hybrid microgrid which I was telling, that is the AC-DC decoupled hybrid microgrid. So that is actually the similar case with this hybrid microgrid DC coupled. But if you are employing both the AC-DC coupled hybrid microgrid, then you have to use certain distribute this power generation on the various terminals. Suppose you have the DC generating source, so you connect directly to the DC, and you have a AC distributed generation, you can directly convert AC to DC conversion, then store it. Same with the, if you see in the right side also, if you have a AC distribution at the AC bus bar, then you have to convert from AC to DC to AC for matching this voltage level from the generating source, and the DC distribution from DC to AC in the storage system. This features actually a main challenge. The main challenge to manage this power flow is that you have a multiple operations are there. So a grid tied situation is there. Second is the standalone system, that is the islanded situation. You have to droop control the system for if you have the multiple generating sources, multiple inverter into place. So if based upon that situation, you have to use this multiple controls into the system, which I will explain in the further slide. So this is the one question based upon the need of the storage into the microgrid. I have given these six statements, and you have to tell me that which statements are true related to this need of storage in the microgrid. Just read the statements, and you have a certain minutes to solve this problem. And if you are getting a as a true or a as a false, just write into the in the chat box that a is true, a or false. After that you can try b. Okay, you have a certain minutes, couple of minutes to solve this question. Okay. Do you have any doubt in between? You can just open your mic and ask me or write in the chat box. Okay. If you got the answer of the first statement, you can write that also. That create a positive impression for me also that you are trying the statements. Okay. Last 1 minute for this question. Anybody who is trying the question, I can give you some of the minutes for reading the question as well. It's already 3 minutes. Do you need more time? Just write in the comment box that yes, I need some time. Okay, then fine. I'm going to read the statements and give you some of the conclusion based upon that. So, first statement is saying that storage elements are crucial in the microgrid to enable the standalone operation or the smooth grid connection operation due to the intermittent nature of the renewable energy sources. That is true. True in what sense? Because you know that this PV generation have certain curve. Starting, suppose this is starting from the 6 a.m. and it can reach till suppose 1 p.m. and then it will fall down to certain time. Suppose this is 6 p.m. Okay, so this is the characteristic. That is the actually this power characteristic at which the this E radiance varies, and based upon the current level of those PV is also varies. Okay, so this is intermittent. Why this? If suppose this weather condition is not normal, so at that particular point, your this curve can differ. Okay, so for that operation, you need certain storage elements which can provide the supply at a non PV generation times. So this storage system can operate when this can discharge when this PV is not available, and it can charge when this PV is available. Okay, so this kind for this operation you need a certain battery banks or the ultra capacitors. Second statement is saying that storage elements can be categorized into two types, that is the capacity oriented energy storage and the access oriented energy storage. That is true. Why? You have actually definition or defined as a storage element into the two types, that is the capacity oriented and the access oriented. Capacity oriented is such that suppose you have installing the battery banks you needed of 10 kilowatt nearly. Okay, so based upon your ability and your demand, you install the 10 kilowatt capacity. Okay, this is the capacity oriented energy storage, and this capacity will be if you charge at particular time, it will be available at a particular standard. You can discharge 10 kilowatt at a particular situation when this situation occur in the high loading capacity times. And second is the access oriented energy storage. Based upon the access, you can actually install this energy storage. Access in sense, suppose you have microgrids are there. You have a microgrid, you have energy storage there. Suppose you have a certain substations, base station, you can also install that access oriented. And this are the two types of, based upon the accessibility and the capacity, you can categorize the storage system. Second is the third statement saying capacity oriented energy storage are characterized by their slow response time and the primarily used for long-term energy balancing to mitigate low frequency power oscillations and the compensate for the intermittency of the RE sources in the microgrid. That is true. That is true because the capacity have a oriented energy storage is a low response time, but it can be utilized for the long term this energy storage for the low frequency power oscillation into the system. Okay, and these examples, that is our fourth is also true, and these examples are this batteries, pump storage, hydroelectric systems, compressed air energy storage system, and the hydrogen storage. And coming to the fifth, that is the access oriented storage devices possess fast response time and are available responsible for addressing short time disturbance into the microgrid by providing high frequency power component. That is also true, and its example, that is 6, is also true, that is the flywheels, supercapacitor, and the superconducting magnetic energy storage are considered access oriented devices because the flywheels and the supercapacitors that can discharge the energy at a certain at a very short duration of time. Okay, but that is not the case with this pump storage and the batteries. It takes certain time to give this power. Okay, so these are the two kinds of storage devices, storage systems into the microgrid, and these are solutions. And I have one more question related to this management of the microgrid. I am giving few minutes to solve this question. Read this statement. There are 5 statements. You have to tell me that which statements are correct related to this management of this microgrids. Okay, Gautam, Raj. Okay, all 5 statements, actually 6 statements are true, Gautam. 6th statement is also true. Flywheels actually a fast energy service provider that is also come into this access oriented because you need the high amounts of power at a short span of time. Okay, please go through this question and let me know if you have any doubt into the reading these statements or understanding of these statements. I request everyone to please try. Please try. Let me know if you have any doubt. That is also important for your this growth of your personal growth also and the professional growth also. You must try. Anybody got the first statement answer? It is true or false? Last 1 minute. Okay, fine. Let me give you some clarity over the statements. So, first statement is saying that control strategy and the power management schemes are critical aspect of the operating of a hybrid AC-DC microgrid, essential for the providing the operation in the both grid connected and the stand-alone modes. Okay. So what is saying that you know already that there are three types of microgrid: AC microgrid, DC microgrid, and AC-DC hybrid microgrid. Okay. So in the all the systems you have is different features. Okay, and you need a certain communication features between the control strategy for controlling or connecting with this utility grid, which is actually AC. Okay, so a certain kinds of managing feature or control strategy is needed between this AC utility grid and these types of hybrid microgrids or AC to DC microgrid. Okay, in the both situation, when it is connected to this utility grid or when it is not connected to the microgrid, micro utility grid, then you have to manage this microgrids in this such a fashion that it can generate the power based upon the voltage level and the current requirement of your system. Okay, so first statement is true. Second statement is saying that in microgrids, the management is divided into two types, into power management and the energy management, based upon the control task and the time scale actually. So you know that energy is power, tip and time, the area between this PT curve. Okay, so the management is actually what you need, that a certain point, suppose this is a T1 time, you need certain power. Okay, so this power, what power to be injected from this microgrid, that is actually defined in terms of this voltage, this power magnitude. Okay, so how much energy requirement, that is actually based upon this PT curve area. Okay, so the utility, the discoms actually takes place, make the certain arrangement inside a system that how much power actually they have to feed to this local loads. Okay, so they define it as a load curve, and this is the such a, this is average load, and this point is a peak load, and you have a certain minimum loads also. Okay, so based upon these three factors, they actually plan in the sense that how to operate. Suppose the microgrid which is locally generating the power have a higher capacity, so then the discom have to curtail the certain power generation, so that they can offer a low amount of power into the system, they can inject the low amount of power into the system. So that is true, second statement is true. Coming to this third statement, actually third statement is saying that short-term power management strategy aim to influence instantaneous operation containing conditions such as voltage, current, power, frequency in the microgrid. That is also true. How you should do, you can do with your certain which I have told you, access oriented microgrid, access oriented this battery storage system or the this energy storage system. And the short-term power management strategy, this also influence the instantaneous conditions such as voltage, current, power and frequency. In the first statement, if you read that, it is saying power management strategy include voltage and the frequency regulation as well as the real-time power dispatching among the different power sources in the microgrid. That is also true. What I have told you in the this PT curve, that is the actually the load curve actually. So how much amount of power you have to inject, that actually have to be forecasted based upon the previous load curves. Okay, so they, based upon that, the system planners actually design their system, how much power they purchase to give this this feeders, at which feeder they have to inject how much amount of current and the power. They all actually plan in the sense that they can provide certain voltage and the frequency regulations for this power management. Okay, so fifth statement is saying, actually fourth statement true, fifth statement is saying that energy management algorithm focuses on optimizing total power production to meet demand in the optimal way. That is also, I have told you that PT curve, that is the PT curve area is actually energy. So by planning this power, you can plan this energy. So energy management algorithm, it actually optimizes this power consumption, power production to meet the demand in the optimal way. Why? Because if the your microgrid is generating a lot of power, then your load which is demanded, actually power which is demanded, so you are in a surplus situation. Surplus situation, you can send this power to the grid itself. And also if the generation is low, if the microgrid generation is low, then you can take the power to meet this load. Okay, so this kind of algorithm have to be there, so that they can optimize the power in the different situations, considering this fuel cost, capital cost, maintenance cost and the mission profiles at the lifetime. Okay, so this is actually the main concept of the management of this microgrid. Coming to our second other topics, that is actually the power management strategies of the different coupled microgrid, AC, DC or the hybrid coupled microgrid. So in the first situation, if you see that this is the AC coupled hybrid microgrid, they have this two systems. One as a grid connector system, second is the standalone system. So in the standalone system, suppose this is the microgrid, and this is not connected to this utility grid. Okay, in this situation, what is there? You have a certain energy storage may be there, energy storage, and some local generation. Okay, in this situation you have to optimally manage this so that it can generate this voltage of 230 volt and frequency of the 50 Hz, which is needed for your appliances. Okay, so this DGs, that is distributed generation, SC is the storage equipment, that is AC busbar voltage, that is the frequency, voltage and frequency can be controlled, and the demand power sharing by this droop control or the master slave power balancing using MPC based method. Okay, so there are certain control strategies are there by which you can generate the power, optimally utilize the power. One algorithm is the MPC algorithm is there, and other algorithm, the time optimization algorithms are there, or the power optimization algorithms are there. And second, this master slave. Master slave in what sense? Suppose you have a certain types of microgrid, microgrid 1, microgrid 2, microgrid 3, microgrid 4. Not microgrid, in the power generating sources G1, G2, G3 and G4. Okay. So what is a master and slave do? Suppose this G1 is a master and the other generating sources are connected to certain inverters. That inverters are working in the slave condition. These are all are the slave. So this master will manage the power which is generated, power from dispatched from this as this G2, G3 and G4 based upon the what is actually demanded. Okay, how it will do? It will do based upon the droop based method. Droop based method, that you have a certain power curve and the frequency, and based upon the frequency and the power, based upon frequency the power needs to vary for maintaining this optimal power volt frequency level. Okay, suppose you want to maintain 50 Hz, so based upon that your powers will be increased or decreased. Okay, and that this DGs and the storage system actually have a different controllers connected to this neighboring islanded microgrids. Okay, coming to this grid connected microgrid, you have a two system can be there: dispatched output power, undispatched output power. Undispatched means you have a banks. Banks means storage systems, and dispatched output power means you can dispatch its particular point based upon this power control mode. Okay, power balancing. But in the undispatched mode, this SC typically on the charging mode. At that situation, you cannot dispatch the power from the storage systems which is already working on this charging mode. Okay, because it have to maintain certain SOC if you are using the battery banks. Okay, and this is MPT control mode. What I have told you, that when the PV generation is very high, suppose it is generating 2 kilowatt at a peak and your load is at 1 kilowatt. Okay, in that situation you where to inject even this 1 kilowatt power, there is no outsourcing power mechanism is there. So what we do, you use MPPT algorithm to generate power at only 1 kilowatt. Okay, so that it can meet this 1 kilowatt. If it is a grid connected system, so then this 2 kilowatt access power, that is the 1 kilowatt, can be delivered to the grid. Okay, so these DCs are operating in the MPPT control. Okay, so there are other situation with this DC coupled hybrid microgrid, that is was for the AC coupled, and this is for the DC coupled. And DC coupled, if you see that this is the standalone or the islanded situation, you have two system is such that there is a DC bus bar can be there, or the AC bus bar can be there. If it is a DC coupled microgrid, you can connect directly DC generating source with the directly DC, and for AC you need to convert this AC to DC, then you can connect with this DC. Okay, so in that situation you have a bus voltage, you have a certain voltage at this terminal, and this AC bus voltage control. AC bus means your utility is connected actually AC, and you have a interfacing components converters for connecting with this AC. Okay, so in the DC bus voltage control, your DGs, SEs, DC bus bar voltage control directly happen with this power balancing and the droop control. But in the AC bus bar control, you need a interfacing component, AC bus bar central control. That inside this, that in between this DC to AC, you have the interfacing converters. Okay, in the interlinking converter, regulate this bus voltage. Okay, and in the grid connected mode, you have a two situation into this also, dispatched and undispatched. Undispatched means SCs are charging mode, DC is operating MPPT, and this interfacing component, interfacing converter, maintain this DC link voltage. Okay, same with this dispatched power output. That is same with this what I have explained. Coming to this other topic, that is the AC DC coupled hybrid microgrid. Here also there are certain situations there, but there is an extra component. If you see in the below section, in the standalone, this all are same as what was the previous in the DC coupled microgrid. But the important point here, you have to understand that interlinking converters on the AC link voltage control mode and or the DC link voltage control mode or the power control mode. Okay, in the previous, you don't have any features or interfacing converters control in between this AC to DC. Okay, but in the AC DC hybrid microgrid, you have this control for maintaining this DC voltage, DC link voltage at a rated voltage, and the AC link voltage at the rated voltage. Okay, and same with this grid connected mode. Here the grid connected mode have a two system, that is dispatched and undispatched. Dispatched had the two system, that is the ILC, interlinking converter DC bus voltage control, and the this DGs and the AC coordination with the DGs for the providing dispatch power balancing. Basically this is a power balancing in the voltage control, and the dispatched output you need to maintain this DC link voltage and the AC power AC bus voltage for maintaining this power control and the ILC power control. Okay, so these are the 3 points I wanted to highlight, that is for generate microgrid, that is AC DC or AC DC microgrid. You have two situations, that is the grid connected and standalone, and you have to control the voltage. Why? Because you cannot connect this AC generating source directly to the AC bus bar. You have to use certain controlling features so that it can generate and resonate with this AC microgrid, that is the 230 volt and the 50 hertz. If this AC generating source is generating at a 25 hertz, so then you have to control and you have to check and you have to transform this 25 volt signal to the 50 hertz signal for the operation. Okay, same with this DC link voltage, this DC coupled microgrid also, you have to maintain this DC voltage also. Why? Because if you are converting from DC to AC, you have an inverter and you are giving this 230 volt 3-phase supply and a 50 hertz. So this DC voltage have to be maintained at 650 to 750 or 800 volt. So for that also you need certain controls. Coming to this last part is that this power management during transition. Okay, you have a two part of which I have told: grid connected system, standalone or the isolated or islanded condition. Second is that when this situation happening, that it is from the islanding, it is moving to this grid connected system. In that operation mode transition, you have also two systems, that moving from grid connected to islanded or islanded to the grid connected. If it is moving from the islanded to the grid connected system, then the control strategy is such that switch off control strategy from the voltage control in the standalone mode to the current and power control. Okay, so if you are connecting this islanded grid with this islanded microgrid with the grid, then you have to check take the P reference into the system, into this control strategy, how much power is have to be injected. Okay, and the uniformed control strategy in both the standalone and the grid connected mode. And the second, when it is moving from standalone to grid connected mode, other thing is the synchronization between this three-phase system. Suppose you have a three-phase transformer, then the phases have to be synchronized. Okay, and if it is a star delta or delta star or star star or delta delta connected system, then the synchronism have to be there. So if it is a plus minus 30 degree, then the opposite also have to be plus minus 30 degree based upon that. Okay, So there are two types of synchronization, that are passive and the active synchronization. Based upon this, how you are how what methodology using for synchronization of this grid and the your microgrid. Okay, and the grid connected to islanded, so there is a very limited kind of strategy, control strategy in that is switching of this control strategy from current to power, and uniformly control strategy from both grid connected and standalone. Okay, so this is the end of this module. So other is the coordination, the classification of this energy management systems, so that it can be operated in the synchronized manner and controlled manner, and it should not overload the system. So for that controlling features in the energy management in the AC distribution, AC DC microgrid, you have it three methods. First method is decentralized, second is centralized, third is distributed method. If you see in the decentralized method, there is no communication between the each layer. Okay, so this is a physical connection is there. So you have a this certain LC, DZs. This is the one microgrid. This another. This is another. In between the microgrid, you don't have any communication and the control. Okay, so each disease are separate, and it can take this actions by self itself and without interrupting the DG2. Okay, so communication network is not needed for the distributed network because there is no communication between the DG1 and the DG2, and the control through the local variable. Local variable means this DG1 can itself is capable of controlling or managing this energy. Okay, and the third is global variable are inaccessible, and the means it don't have any features of controlling the DG2 based upon any operation. Coming to the centralized system, if you see that there are central communication between the all DGs. All distribution system can take the independent decisions, and also it have the permission or the accessibility of the global variables. Global variables is such that DG2, DG3, DG4 and DGN, and the communication feature is there. Communication network is needed, central node and the operator is there, which is controlling the all the DGs, and access to the global variable. Global variable is there because the DG1 knows the variability in the DG2. And there are certain problem is since this is a problem of single point failure, because the DG1 have to be adjusted based upon DG2. If this communication got interrupted, this communication central communication got interrupted, then DG1 or DG2 get fail. They get fail because there is a no central communication, and it have the accessibility of this global variable, and this situation is also not reliable. Okay, so what we done is we have a distributed method. In the distributed method, if you see that there is a central communication is also there between all the system, and the distributed communication is also there. It means that DG1, DG2, DG3 can communicate through the central controller, and DG1 and DG2 can also participate in the communication, the control in the by self also, in between also. So the communication network is needed, and the peer-to-peer communication is also there because DG1 has a communication with the DG2, and the lesser communication channel than the centralized. Why? Because there is a central communication is there, which is actually not desirable. Why not desirable? Because DG1 is DG2 is actually in communication. Okay, you can also remove the central communication into that. Fourth point is that no problem of single point failure. Suppose this DG1 and DG2 communication got failed up, then DG2 and DGN are still in communication. They can manage the power delivery or the consumption. And the fifth point is that accessibility of the global variable. It have the accessibility because all DGs are in communication. Okay, so these are the three types of communication features are there, and in between this physical layer and the communication layer of this AC-DC or AC-DC hybrid microgrid. Coming to this decentralized method, because that is the most robust method. Okay, so if you see that interlinking converters with the decentralized method, how their operations are there. So in this method, this interlinking converter mostly operated based upon the Droop laws. Okay, DC microgrid operates in the voltage droop, and the AC microgrid operate in the frequency droop. So if you see that this is the AC microgrid and this is the DC microgrid, and in between you have a interlinking converter converting from AC to DC or the DC to AC. You have a interlinking capacitor converters, and you have a LC filter for reducing the harmonics which is injected into the system. And you can use this DC bus bar for convert to DC to AC, and you can utilize that. Okay, so this operation of this DC microgrid, if you see in the right side, it is operating into this droop control, voltage droop control. Voltage droop control. If you see that this is the DC source is there, this is DC link, then it is converted to this. If you see that this is the DC, then it is converted to connected to LC filter, then it is connected to the DC bus bar, and DC bus bar is connected to this LC filter, which is connected interlinking capacitor. Same with this AC microgrid. This DC generating source is there, DC to AC conversion happens, LCL filter is there in between, then the voltage booster can be there, that is using the transformers and all. Then you have AC bus bar, it is connected to this here. So main thing is that this DC microgrid can operate separately and AC microgrid can operate separately. That is actually the decentralized control. One, this have the communication through interlinking converters. So this is a kind of system is known as decentralized control communication mechanism through the ILC control. Okay, and the second point is that this droop control laws. If you see that this is the interlinking converter, converter is there, and this is the DC microgrid droop, and the right side this is the AC microgrid droop. What I have told you that DC microgrid basically to manage the voltage, and the AC microgrid generally to manage the frequency. So based upon the frequency operation, this power is being a steady state point can be reduced or can be increased based upon the frequency which is frequency change which is happening into the system. And if you see in the DC side, this DC voltage have to be changed based upon the power consumption level. So in between this interlinking capacitor enforces that what is the change in this voltage can be proportional to this frequency. Why? Because if the power consumption in the AC side got reduced, it means that frequency will rise. That frequency rise will get reflected to this interlinking capacitor converter. So based upon that, this DC generating power will deliver lower than the which is demanded, which was initially at the steady state. Suppose the frequency this power generation got increased. It means that frequency got increased, and in this situation this DC microgrid will have to take the extra power for operating. So it will increase the voltage based upon that, and this extra power get absorbed into this DC microgrid. And if there is a load also, it can be distributed to that load also. Okay, so these are the basic operations and this droop mechanism inside of these two systems. And coming to this hierarchical control, what I have told you that there are two layers. One is the physical layer and second layer is communication layer. Communication layer is above of this physical layer, so that the power of proper control and proper communication can happen in between both the system. So what happens in the hierarchical control architecture, if you see in the right side where my cursor is there are three layers: primary layer, secondary layer, tertiary layer. In the primary layer, faceted control loops are there. It happens into this microsecond to millisecond. Okay, here the primary layer control is the PQ based control, VIF based control, islanding detection, and the protection. Okay, in the second, if you see this second layer, it is slower control loops, seconds to minutes. Okay, V by F restoration, synchronization, and the power quality issues. And in the tertiary layer, if you see, there is a certain mechanisms are there, that is a power exchange, optimization, grid interface, unit commitment, optimal dispatch, and the DSL. Okay, distributed system monitoring, and the grid operator and the energy market, they have already been in communication with this into this tertiary layer. Okay, so tertiary layer communication is very important with this grid operator. Then it flows to this secondary layer, then it flows to the primary layer. Okay, because first thing is that you need the power, you need the power of certain voltage, certain frequency, and certain harmonic level, below for harmonic level. Okay, so that point is actually have to be managed through this grid operator and the tertiary layer communication. Okay, and this is the slowest communication in between minutes and the hours. Okay, so this is also a kind of system, and if you see this in the central part, that is a microgrid generation. Microgrid generation, that is AC microgrid. In between you have interconnecting converters, then DC bus bar, and which is connected to this DC microgrid. And in the left side, if you see that, they have a grid is connected to this transformer, then to this point of common coupling. Okay, so synchronization, grid mode, islanding, and the islanding, then these are the operation mode. Operating mode is such that grid connected, islanded, and moving from islanded to grid connected, or moving from the grid connected to the islanded situation. These are actually the operating modes. So coming to this ILC with the distributed control method, if you see, this is the AC line, and this is the DC, this another AC line. And if you are controlling this mechanism, because you have a certain DC loads are there, DC generating source are there, DC generating source DGs are there. After that, you can convert into the AC lines, and you can feed this AC load. And actually this is wrong, this is DC line. So based upon this current level and the voltage level, this communication between this both the systems. Suppose in the left side, if you see DG1, DG2, DG3, in the communication with this communication network 1, 2, 3, and giving the power of variables such as EI, energy, Q, reactive power. Based upon that, this information exchange happens between the AC and DGs, and then it is transferred to this DCs through the communications. Based upon that, voltage and current being controlled at DG4, DG5, and DG6. Then the power based upon that P4, P5, and P5 being distributed. Okay. So this main crux is that this decentralized method uses local variables for control. However, due to unavailability of the global variable, the method may suffer from inaccuracies in inaccurate power sharing. But in the centralized technique overcomes from the inaccuracy. It have this global variable parameters through this higher communication, and is suffer from the single point failure. But the distributed technique are the more robust. This distribution technique utilizes reduced communication channels. It offers the similar performance as the centralized, but it have also this peer-to-peer information exchange. Okay. So other architecture of the hybrid microgrid are, this is the additional DGs and additional AC DGs. If you see that this is the utility grid, it is connected to this point of common coupling, and it is connected directly with the AC subgrid, hybrid microgrid. And for connecting this DC subgrid, you have to connect this interlinking converters. And same with this utility grid, that additional ACs are there. Then you have to use, suppose you have a 60 Hz generation, but your normal operation is 50 Hz. Then you have to convert. You have to convert it from the 60 Hz to 50 Hz. For that, what you need? You need, suppose you have generating AC and at a 60 Hz. Then you have to convert into DC. Then DC to again DC, you have a certain interlinking capacitor. Then DC again to AC at 50 Hz. Okay, so that point is also important to this architecture. So what are the important points is that it is a improved power balancing for the single and three-phase system achieved, enhancing the voltage quality at the point of common coupling and the output terminals. Proportional active power serving between the MGs help in better utilization of the power electronic devices. Futuristic system to integrate locally available but diverse in the nature distributed generation. and the different levels of voltage ranges can allow loads integration of the diversity. So main crux is that main major point is that multiple devices you have to connect, multiple generator systems are there, you have to connect and disconnect based upon the situation. For that you need a certain central communications, and distributed communication is the most robust. Okay, so what are the possible research areas for this system? Actually, self-healing power systems, that is actually the techniques for grid forming in nature, its application in the self-healing, because two systems which I have explained, that one is the grid forming and second is the grid feeding. Okay, grid feeding mode take the P reference as a one of the parameter in the control strategy, but in the grid forming it takes the voltage and the frequency into the consideration for the forming the grid itself. Okay, so what are the multiple techniques are there? That is one of the research area. Its application in the self-healing power system facing the natural the man-made disaster could be demonstrated. And second is the cyber security. Cyber security is the one of the major issue. Is the one of the major issue in this, and a lot of research is going on into this field. So because you have a communication layer and the control layer. Okay, so main, if you have a certain things into connected to the internet, then the problem comes. If you have a no internet, no communication, then the cyber security issues can be avoided. So this is a one of the potential research directions. Second is the malware detection. If you detect the malware at a early stage, you can mitigate from the problem at a very early stage of the this operation. So detection is also a one of the potential research. And second last is the mitigation of the resiliency. How, if the malware comes into your system, how to remove that malware, and how to make your system robust, and uh, make the system to work in the normal condition. Okay, so these are the potential research areas. Coming to this other topic is that next module is such that you have a microgrid modeling in the simulation, because you don't have this wind turbines or microgrid generation system at your home itself or any other places. You have to have a certain access to a certain tools so that you can simulate it and study the behavior, and study the what are the components are there, how their control features are there. For that you need a certain real time simulators such as Opel RT and Typhoon HIL for the hardware in loop. So there are multiple kinds of system at which you can test your real models and in a real time. Because if you see in the MATLAB, when you run a simulating platform, it takes lot of time. Suppose there is a 10 second is there, it takes a 1 hour to run if your system is very complicated. So this is not a real time. But if there is a Opel RT is there, it makes the 1 second in a virtual environment as a equal to the 1 second in the real environment. So that system is needed for the this operation and observation in the real time itself. So detailed modeling and the simulation of the microgrid, it helps in the rigorous analysis and identifying the key challenge and the feasible solutions. Okay, and this transient simulators, that is the electromagnetic transient simulators, have the real-time digital simulator RTDS, and certain voltage ranges, certain frequency ranges, and based upon that this controlling has been tested. So major advantages of this microgrid modeling and simulation relates to system, that is the continuous real-time simulation and the hardware in loop. This I wanted to explain in the very detailed sense, that is the what is the actually this continuous real-time simulation and the what is the hardware in loop. Continuous real-time simulation is that if the microgrid analytical studies can be performed much faster with the offline simulation platform. What I have told initially also, the MATLAB, you have a certain monitor is there and a central PC is there where this MATLAB model is being dumped. After that you can feed connected to this Opel RT, and where this system can run. You have IO port also there, so that you can simulate the real-time features into this offline grid system. And in the continuous real time, the simulated system can operate in manner like real microgrid system. And this, as the simulation parameters are modified and the contingencies are applied, the user can watch the microgrid system respond in the real time. That is true, because you cannot create a three-phase fault into the directly going to this grid. So what you do, you can simulate and you can create the fault into the system, and you can see the abnormal behavior into the system in the real time. Okay, for that you need the continuous real-time simulation. And second is that this is the hardware in loop testing. In HIL, it have the capability of the real-time simulator allowed to design and operation of the microgrid control protection power devices to be evaluated under realistic operating conditions before they install. Suppose in the last in the down portion, if you see one figure I have given, this is actually a microgrid, this Opel RT setup. This is also written here also, this is Opel RT, and their model is inside of this laptop. So this Opel RT have this FPGA for the real-time simulation. Here the traction inverter circuit is being tested. It is taking winding voltage and the winding current into the system. And if you see that, you have this MATLAB Simulink controller model, which can take the feedback and send this feedback and send this PWM signal into the system. So suppose you have generated and model a control system. Suppose you have modeled a control system and you wanted to test that this control system is robust or not. So what you do, you make a MATLAB model of your grid system islanded model, and dump into this Opel RT. Opel RT have certain IO ports. Suppose your control is such that it takes the analog input and gives this digital output to the pulses, to PWM pulses, to this converters. Okay. For that, Opel RT gives the analog signal. You have to generate the analog signal from the Opel RT and give to the control signal and take the PWM signal and again feed into the Opel RT. So this is a system of kind of real-time hardware in loop. So you taking the control into the action and taking again the Opel RT, this actual environment. So that is actually the main desirable feature. Here I have wanted to show one example which has already been explained into this lectures itself. This is the AC microgrid case study. You have a certain grid connected mode. You have a two modes, grid connected and the islanded mode. And this is the point of common coupling between this three-phase 480 volt grid. And you have a circuit breaker. And this circuit breaker is connected to this AC bus bar, and this AC bus bar is connected to some battery storage, diesel generator, AC loads, and the PV. Okay. So what I have told you that PV may operate on the MPPT and may not, based upon the loading condition. And in this mode, the grid is not available in the islanded mode. That is true. And the battery either charge and discharge based upon the reference command. Reference command is such that in a voltage and the frequency. And this DJ generator is operated in asynchronous mode. Asynchronous means why? Because the diesel generator is a second priority load, priority generating source. When the PV is not available, when the battery is not able to supply the load, then you can use these DGs. Okay. And in the grid connected mode, you always use the PV operate in the MPPT, because if the extra generation is there, you can send directly to the grid by using the hybrid inverters. Okay, and the battery either it charges discharges based upon the reference command. Reference command is such that maintaining the VDC and the P reference, which is taken from the grid, and the DJ generator, it helps in the voltage regulation. Okay, so coming to this control strategy of the PV and the battery, it have a certain control feature. Suppose if you see that what I have told in the initial, that path transformation and the class transformation. So it is easy to actually design a control system in this DQ frame or the alpha beta frame, because it is a non-synchronously rotating frame except DQ frame, and this alpha beta and the DQ frame is a time independent situations can be handled. Okay, so here if you see that P reference and the Q reference has been taken, and this ID and the IQ is given. based upon this ID star and IQ star, and then it is compared with this omega LIQ. Omega LIQ, this actually comes with this feed forward method for controlling controller design. So it takes the feature of the IQ components into the D, and D component into the Q part. Okay, then it is converted to DQ to ABC using this Parks transformation, inverse Parks transformation. Then PWM is generated, and then it filtered to the inverter. Okay, this is the basic control design for this inverter control. Okay, second is the converting to this control feature of the diesel generator. Diesel generator have the governor speed governor which regulate the speed and hence frequency of these changes. Okay, and the mechanical input of the synchronous machine rotor, which can be adjusted based upon this what is actually needed. And the second is the excitation system. Excitation system is such that suppose you have a suppose this is a generating source and this is a actually AC bus bar. Suppose the E is higher than the E actually rated. So the overflux condition can happen, that over generation is there. So what I have told you, that this Q reactive power is strongly coupled with the voltage, and the P power is strongly coupled with delta. Okay, and Q is weakly coupled. It means that delta Q by delta is nearly equal to 0, and delta P by delta is nearly equal to 0. It means that any change in V is reflected into the Q, and any change in the delta is reflected into the P. So in the overexcited generation, overexcited system, synchronous system, it have a higher voltage. Higher voltage means that it have a higher reactive power. So it inject that extra reactive power into this grid, okay, into the system. But in the under-excited synchronous generator, if the voltage is lower than the what is rated, in that situation, it needs the reactive power for maintaining the voltage at the rated value. Okay, for that it absorbs the reactive power from the system. This is the most important part. And second, when the normally excited, it means that it is operating at a unity power factor. There is no need of reactive power for operation of this system. Okay, so coming to this result part, if you see that first one is the grid connected mode. Grid connected mode means your system, your whole microgrid is connected to the grid, and in this case one is that no distributed energy sources is there. No distributed energy sources such as PV, diesel generator, battery is there in this system. It means that grid is connected, but there is a no microgrid is there. It means that you are all the power which is generated is 0. If you see here that 5 e to the power minus 9 current, that is actually nearly equal to 0. Same with this PV generation, that is 9 equal to 0. And generator current is 2 e to the power minus 9 nearly equal to 0 maximum, and it is also 0.85 or 0.47 nearly equal to 0 grid current. So this is a point of common coupling voltage. If you see that it is also very low, that is a 0.39021 kV is there. So this kind of voltage is there. So all the current is coming from the grid for the consumption of this load. Okay, for the operation on the consumption inside of this load, all the power is coming from this point of common coupling. It means that it is maintaining the 390.21 voltage from the grid, and also the point of common coupling breaker is taking the current such as the 854 point something. Okay, so all the power is coming from the grid to the load when there is this no PV generation or the battery storage or the diesel generator is there. And if you see the second case that no DERs is there, no distributed energy generation, but additional load switching occurs. Okay, 0.5 volt megawatt to 1 kilowatt, 1 megawatt. So if the certain load increases there, power consumption will increase. So grid have to supply extra power to this load. So at this point of this CB, which is connected between the grid and the load bus, it current got increased, but the voltage is constant. If you see that voltage is constant, but the sudden increase is current is there. Okay, when the load got switched. Coming to this third part, that is when the DER is switched on and the battery set is in charging mode. in the off-peak hours, and the PV is operating in the MPPT, and the general generator operating in the voltage regulation or excited. So in this situation, if you did the PV is also generating 1 k power, 1000 amperes. Battery is generating also certain power. Generator is also delivering some. Battery is taking the power because it is charging, but the PV is operating MPPT. It means it is injecting the power into this grid and this load, so that if you see in the load, it power got reduced, its voltage got reduced from the grid, which is coming from the grid, because the local generation is already, it is charging, but it is PV and the DC generator is supplying the power to the system. And the multiple cases can happen that when you operate in the battery side is obviously discharging mode, PV is in insulation mode, or not in operating in the MPPT mode. This DJ generator operating in the voltage regulation. So that kind of other systems can also there, based upon that current you differ. But the voltage remains constant because it actually addressed with respect to this grid, because it is grid connected mode. Okay. And the P reference matching. Okay. So that situation, if you see the islanded, if you see in the islanded mode, the current which is being taken from the to this load, actually taken from the battery, PV and the GJ generator, and all the currents is being supplied. No current is being taken from the grid. If you see in the down figure also, it is current is nearly equal to zero from the which is coming from the grid. So these all are simulated into the real-time simulator. So case 2 is there when the battery main grid disconnected but the battery is charging. So the load which is coming, power going to the load will reduce. Okay, so that is also the one of the situation. The other situation is also there when the switching can happen. Okay, so these all are actually the one other kind of other kind of situation where the things can happen. Okay, so there are other situations also there which I don't want to go in the further discussions, that you are in the further this tutorial session I will explain that how the operations are there with the DC microgrid situations, how you can operate and how you can test. So main crux here which I have shown you, let me take one slide to make you understand from there how to implement and how the actually implemented into the real-time environment. So let me take one slide. So suppose that there is a company called DY. DY manufacture hybrid inverters. DY manufactured hybrid inverter which can have 3-phase or single phase. So this inverter is such that this is a, suppose this is a DY inverter. It have a certain ports for taking the power, sending the power. So it is connected, suppose this single phase system. So it have a certain AC out which is connected to your home. Okay. So and also it have a certain PV connected system also. It have take the power from the PV and have MPPT, and after that it converts inside of this using inverters and fed to this AC out. And one more feature is that it is also connected to the grid. There are certain ports are there from which it is connected to the grid. Suppose the PV generation is higher, it can automatically give this power to the grid depending upon the home load. Suppose the excess generation is there, so PV minus P home can be go to this P grid. Okay, and this PV also have this operation of this islanding situation also, based upon that it reduces power or increases the power, and based upon this MPPT control. Okay, so this is actually one of the hybrid inverter which is actually in field to operate, which our lab is also doing for this demonstration of this hybrid control and the hybrid mode of operation of the kind of PV battery and grid also connected to a single system. And we also trying to want to do this wind turbine based system also to conduct in this hybrid inverter itself. So this is the main crux which is actually happening into the our lab also, which you can also you can also make your career also in that by high study or anything. So if you have any doubt, you can ask me. And also that there is a gate result came just now, and you may be familiar that you can also filling the forms of the IITs for, NITs for the PhDs and MTech. And you have any doubt related to academics or related to this application process and all, you can contact me or you can ask me right just now. And if you have any doubt right now for the interviews and all, how it happens and all, if you have any doubt, you can ask me now. Okay. You are free, feel free to ask me, and you can also open your mic and ask me. Okay. Because I'm already here in IIT Bombay, and I have also given the multiple interviews at the various IITs. So, multiple selection I got that in the IIT Delhi, IIT Bombay, IIT Roorkee, IIT Kanpur. So I have much experience that how to face the interviews. If you have any doubt, you can ask me. And in the career prospect also, how to approach, how to make CV, how to make resume, how to highlight that, and how to where to go in the current scenario. You can also ask me that, because we our lab also have the multiple collaborations with this Tata Power and all. Okay, you can ask me if you have any doubt. Devendra Gautam or ma'am, if you want to ask anything, you can ask me related to subjects also. You can write in the chat box also. We have 5 minutes more before ending this session for the today's lecture. Are you facing any problems solving the assignments and all? Anybody can answer? Okay, Gautam is asking that, sir, please share some tough situation which you feel at the time of interview. Okay, let me explain you one of my interview during the IIT Kanpur, which I am giving in the Sustainable Energy Department. Because I have done my MTech from IIT Bhilai, and after that I have given the interviews. So in the IIT Kanpur, because I was not in touch with the power systems and the power electronics, because my area was actually in the control design. So mostly I'm focusing on this smart control architectures. So I am not aware of the many concept of this voltages, powers, and the microgrids and all. So in that, they have asked me some of the situation that suppose they have asked me that what types of wind turbines are there. So there are multiple types of wind turbine, that is type 2, type 1. But main thing is that if you are not able to answer the question, then make sure that you should say no. And always share them that what your situation was that, and always highlight that what is your strong points. Okay. So interview always go in that direction in which you are comfortable, because interviews process are for that, for accepting the candidates, not for rejecting the candidates. Okay. For accepting the candidates, they also have a certain parameters. And if the parameter is not suitable for you, so they can adjust the parameter based upon your situation. Okay. In that also, I was not knowing the what kind of turbines are there, that is type 1, type 2, type 3, and type 4. So I told him that I am more comfortable in the control architectures of that. Inside of this type 1, how much control, what kind of control are there? Well, mostly I work on this DFIG control. So he asked me questions related to this DFIG control and battery management systems, and all the ultra capacitors, how they are, you are sharing the power, how the AC/DC controls are there. So my interview went in the positive direction because I have shared my problem with the interview. Okay, so that was a one of the tough situation. And in here in the IT Bombay also one of the tough situation was there because I have applied here in energy science department, electrical engineering department, and also in this system and control department, and I got the selection from all the three departments. What was happening that when the this system and control interview was there, then at that particular situation the energy science written was there, so I have to manage the both the things at a time. So in that situation also I have asked to the professors that what to do in that situation. In that situation they have told that I am postponing or preponing your interview. So these professors are very 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 lenient, and they understand the situation and the problem of the students. Based upon your comfort they shift the interview, or they can consider this things that how to make you comfortable in that situation, because they want the brains, best brains in the all over India, from the all over India. So they actually needed that. So from that they can make you comfortable, make you feel better for their situation. Okay. Okay, Gautam, I think I have answered your question. If you have any doubt, other doubts, you can ask me. Last 1 minute is there because I have to do one experiment in the lab. Okay, you can ask me. Okay. Okay, Gautam, you can ask. Can you discuss some of the importance of the cybersecurity in the smart grid and how it's addressed? Okay. So, see, Gautam, there are multiple things are there. Multiple things in what sense? Suppose there are communication links are there. Communication links between the multiple input sections, multiple output sections. Okay. So suppose I am want to operate a circuit breaker from a remote location. Okay. So in that situation, it can happen that some malware can enter into the this line itself, so that it can hamper this information which I am sharing. Okay. So this issue can be happen. Suppose if you take the example of this Tata Power, this grid failure in this not large scale but the small scale grid failure in this Mumbai itself. The Tata Power is handling the power, this discom. So this was a major challenge because the sudden power interruption can cause a multiple devices to failure, because in the IT Bombay itself we have a multiple instruments which is of crores rupees. So if the sudden power supply gone, so what happened to that instrument? You need that the cyber security, cyber physical system into your domain itself, that with the discom system, so that they can address, they can mitigate, they can detect this malware, so that they can remove at a early stage of the time. Okay. So these are the one of the situation that how they test that they actually create an attack in the lab itself. They try to attack the situation where which is happening into the microgrid, and they try to analyze that what actually system can hamper and how the components can behave during that situation. So they make the certain strategy. Based upon that they actually control the system, they can maintain code, and after that they can come to one of the solutions. Okay.
Yes,
So
sir. Yes, sir. Now I understand, sir. Thank you so much, sir.
I think I have answered the question, Gautam. Okay. Okay. Thank you very much, Gautam, and
Okay,
thank you,
sir.
Naveen and other guys. So thank you very much. I am in